criteria analysis, I would like to mention two methods, and as I already told you yesterday, I will present you some basics. Then first we will solve the problem in Excel spreadsheet, and the third step will be solving the same problem using Python. So this will be the order of our work today. So I'll start with some short introduction with practical example, and then we will see this example also on spreadsheet. Okay, this is my basic screen, so I will share my screen and my presentation with you. I just need to see this view here. Multi-criteria analysis. There are two main goals of making decisions. First goal could be choosing the best alternative, like find the best object or solution, or create a ranking of objects or solutions. And this is one of the goals of decision making. Another one is searching for optimal value of variables. So find the best value of variable, parameters, and indicator. These are the two main goals of decisions in decision-making process. So when we are facing some decisions, while searching for an optimal value, here we've got the example with a capital structure. We've got here two criteria: taxes and cost of financial distress. In this graph, we've got it presented in a graphical way as these two lines, the purple one and the green one. And basically, the task is to find the optimal leverage ratio. So the optimal point at which no, not point, the structure. Optimal structure of capital. So different types of investments that we have. Some of the investments have a higher risk, but also the higher return ratio. Some of them have lower risk, but also lower expected financial income. So the key thing is to find the optimum point, how to divide our money into those two types, for example, of investments, to get the best result, taking these two criteria into consideration. So taxes, cost of financial distress, or any other criteria we will adapt. So in this case, two criteria. Choosing best alternative. We've got few solutions. We've got few options. In this case, we've got example with cars. Different models, different brands, makers of cars. Of course, price is not the only criteria we take into consideration while choosing a car. Of course, price is very important, but there are also other factors that we take into consideration while choosing a car for us. So that's why multi-criteria analysis, because we've got many different factors to be taken into account in our analysis. What is the typology of optimization problem? So how can we divide them? With regard to the goal of the optimization problem, we've got two types: searching for optimal values of variables, or choose the best alternative, or creating a ranking of alternatives. So we already mentioned this at the beginning. So the goal of optimization problem, the goal for decision making. With regard to type of variables, we can have problems with continuous variables and problems with discrete variables. With regard to number of variables, problems when we've got only one variable, which should be easy, and problem with more than one variable. With regard to presence of some constraints, sometimes we will have some constraints, some boundary conditions, some additional features, some additional parameters that must be fulfilled. And sometimes there will be no constraints. With regard to the method of ranking creation, we've got two types of methods based on criteria function. And so we have some variables, and we've got a function that will return us one single value according to which we can sort or rank the observations, or based on pairwise comparison. So we are not like counting the more or less objective quality function value, but we are comparing objects one with another, and then we are choosing which one is better. In the second approach, we often can identify the criteria that we haven't thought about, because we just think about what we prefer, but we don't know sometimes, or we are not wondering why we prefer one option against another. So like, for example, with choosing a car, we can, of course, identify some criteria represented on different scales, because it can be like numerical values, but it can be also like nominal values, or like logical, that, for example, this car has something, this doesn't. And then we can calculate the quality function and rank cars according to this criteria. But we can also make a list of possible cars, compare first with the second, and compare the winner with the third, and so on and so forth. Then we are not thinking about the criteria specifically. We just have like the object as a whole in our minds, and then we can choose like the best for us in some conditions.
Excuse me, could you please give us an example about the discrete variables?
Yes, I can give you example. Continuous, okay, discrete, let's say they are like in opposite maybe to continuous. This will be numerical values, like the okay, data that takes only certain values. So for example, rating, yeah, when we've got opinions and we rate the opinions, rate the product while giving the review the opinion. So we've got usually like a scale from like, I don't know, maybe 0 to 5. but we don't have it like the continuous. So like as a customer who's giving the opinion, we cannot put like 2.3. We've got either 1, 2, 3, 4,
Okay,
5.
okay, understood. Yes, okay, thank you.
Yeah, so continuous, we get like the full continuous scale real values, while discrete only certain values from the list. Okay. Types of variables in decision-making process. How can we perceive the different variables that we should take into consideration? We've got stimulant variables, for which we prefer the maximum values. So, for example, in a case of car, what could be a stimulant variable? Have you got any your ideas about car? If we are talking about buying a car, what would be the stimulant variable? So the variable that should take the maximum value.
The power.
Probably the power would be the value that we wanted to have, like the maximum value. Yes, the power will be such example. The stimulant variables, we prefer minimum value for those. Any ideas for buying a car? What would be a good stimulant variable?
The color, maybe?
No. Color, if I understand you correctly, color is a nominal variable, which would be difficult to represent in values, because for color, we would say that we prefer like
It's not
certain color.
numerical.
Sorry, can you repeat?
It is not numerical.
Yes, it's not numerical.
Okay, okay.
So it can be represented in a numerical way. There are ways of representing non-numerical values in data analysis. I don't have it, I think, in this presentation, but I can definitely tell you if you want about some methods. But in this case, okay, I haven't mentioned about it. We want to represent all the variables in a numerical way. But there is definitely some feature of a card that we wanted to have the minimum value, not the maximum. Any ideas when we are buying the car, which parameter we want to have like the lowest value?
Regarding CO weights, I don't remember it in English to say that. To have low carbon
Emission?
yeah.
Yes, probably this would be one of those criteria. But also, okay, and I forget this time the English name for it. But let's say the fuel usage, how much fuel the car uses per 100 kilometers. This is also one of the features. I forgot the English word for it, but definitely we want it to be like the lower scale. And nominant variables, a given value is preferred. In this case, for example, we can have, I don't know, number of doors. We prefer, I don't know, we are looking for 5-door car. So we don't want to have less, we don't want to have more. We want to have exactly 5-door cars. So this will be nominant variable because we expect the exact value. In problem solving and decision making, rarely we will have the situation in which we will have a dominant solution. So the best solution, taking into consideration all criteria, the optimal solution, dominated solutions means that there are better solutions. So existence of a dominant solution is a very rare and uncommon case. Usually, two or more solutions will have the same rate or very similar rate. So if we have the problem in which we've got dominant solutions, we are safe because we've got the best possible option and we don't have to think much about solving the problem because with dominant solution, we already have the solution. But in most cases, we don't have it. So we need to take all of the criteria into consideration. So there are, in this case, for example, we've got, okay, here we had two criteria. The axes are not described, and maybe I haven't mentioned about it. So in this case, assuming that we've got only two criteria, because one axis is one criteria, second axis is second criteria, usually we will probably have more criteria, but it is easier to depict it in a two-dimensional scale. So the solution D is best in both criteria. And the remaining solutions has worse values in case of both criteria. In this case, let's say that x-axis represents first criteria and a y-axis represents the second one. So solution C is best taking into consideration the second criteria, but when we take first criteria into consideration, solution D is better. So we've got no dominant solution in this case. We've got, of course, some dominated solutions because they've got worse values of parameters in both cases, like A and B, but both C and D are not non-dominated solutions, but neither of them is obviously superior than the other. And in economy, there were Italian economist and sociologist Wilfred Pareto, and he, among other his achievements, he defined the Pareto optimal solutions. So these for which there are no solution better with respect to all variables, solutions better with respect to some variables, and simultaneously worse with respect to other variables. So these are Pareto optimal solutions. This for which there are no better with respect to all variables. So when we've got this dominant solution, or solutions better with respect to some variables, and simultaneously worse with respect to other variables. So in this case, we've got two optimal solutions in Pareto definition. They are both better with respect to some variables, but in the same time, worse in case of other variable. Pareto frontier is a set of Pareto optimal solutions that creates a frontier for those that are not optimal ones. So the red ones here are all optimal in some sense, while the green ones are not optimal solutions. Data processing. In this case, we've got some observations characterized by 5 variables. I don't have it here on this table. I must check if I have it somewhere described what the observations are, because I should have it. So 10 observations, denoted O1 to O10 objects. Then first variable is stimulant. So we wanted to have the maximum value. The second variable is also stimulant. We prefer it to have the highest value. The third variable is the stimulant, so we prefer it to have the lowest value. And then we've got two nominants. First of which the preferred we prefer this value to be in the range of 3 to 7. So it don't have to be like the nominal value, don't have to be single value, it can be a range. And we've got second nominant value, and we wanted to have the exact value of 150. And these are the values of variables for each observation, for each object. In the same time, all these variables has assigned weights. So information how much from the perspective of the person making the decision, this variable is important. All of these variables are represented on different numerical scales. So if we want to be able to compare them with each other, their influence on the final result, we have to perform the normalization. And this is the formula for normalization on stimulant variables. So we take this variable and we've got this variable minus minimum variable divided by maximum minus minimum variable. This is the normalized value for stimulants. For the stimulants, we take in the nominator not x minus mean, but max minus x, because the minimum value is preferred. So a different formula for normalization. For nominant variables, we've got let's say more complex formula, because in this case we want our value to have the variable to have a certain value. So we've got different formula for values lower than expected range and for values higher than expected range. And if the variable is within the range, we've got a different way of calculating it. In some models, in some approaches, only stimulants are expected. So here we've got also the formula for converting the stimulants to stimulants without scaling them. So we've got the formula how to convert the value. Some methods require only stimulants. So of course we also have the formula for converting nominants to stimulants without scaling them. In our model, we had weights. So the information of the importance of each variable. It is expected that weights will be expressed from as a values, real values from 0 to 1. So basically, we could express them in percents, for example. And this is the formula of how to normalize weights in our in multi-criteria models. So in this example, we've got original data before normalization, and these are values after first normalization, conversion to stimulants, with normalized weights, and and values are normalized. So these are the data after all transformations. And now we've got ranking creation, and I mentioned that we will use two methods. We will certainly start with the Topsys method, which is one of the methods based on pattern of development. The idea of the pattern of development method is that we need to define a pattern of development, which is the I forgot the word. Let's say the artificial object that represents the highest possible values in all criteria. And having this artificial object, we calculate the distance for each object and this pattern. Then we can sort our object in order of increasing distance from the pattern. So basically, the closer the observation to the pattern, the higher in the ranking it will be placed. And one of the creators of this approach using pattern of development method was Zdzisław Helwig, who was Polish economist and statistician, and he proposed this method in 1972. So how to calculate the pattern of the distance from the pattern of development? First, we've got pattern, which in this case is maximum value from all the variables because they were all transformed to stimulants. Then we have our weights. So we are counting weighted Euclidean distance for each object. This is the first step. And then we sort objects according to this distance from the smallest to the largest distance. So if the object is closer to the pattern, so the distance is smaller, the higher in the ranking. In this case, the best object in the ranking is 6. However, the next object 4 is close. Another method is anti-pattern development method. In this case, we define anti-pattern, so the, once again, artificial object that represents the lowest values for all criteria. And once again, we calculate the distance from this anti-pattern. So anti-pattern this time zeros because we've got all stimulants. These are distances from anti-pattern, also weighted Euclidean distance, so the same method. But this time we sort them from the highest to the lowest. So we expect our best solution to be as far away from the anti-pattern as it can be. And once again, we've got 4th and 6th object as the best ones. And then there is Topsys method, which takes into considerations both pattern and anti-pattern of development. So for this method, we calculate the coefficient of quality, which is calculated as distance to anti-pattern divided by sum of distances to pattern and to anti-pattern. And then we sort objects in order of decreasing indicator. So this indicator represents like coefficient of quality, so we expect quality to be as high as possible. These are a few bibliography resources for Topsys method. So in this case, variables represented by columns and objects are represented by rows. So the same structure as in the previous examples. First, second, data normalization. Then we've got weighting of data. We are not using nominant variables in Topsys method, only stimulants and destimulants, and there are like differences. Because for pattern, we expect them to be the distance for stimulants from pattern, we expect them to be lowest. And for destimulants to be the highest. And for anti-pattern, stimulants we want close to anti-pattern. So this is distance, so that the opposite of similarity. And sorry, I need to mute my phone. And for anti-pattern, of course, the opposite. Then we've got distance calculation from both, from pattern and from anti-pattern. And then the calculation of coefficient of quality. Then we can rank objects. So in this case, we are starting with original data. We've got stimulants, destimulants, nominants. We need to convert nominants, to stimulants, because there are no nominants in Topsys method. Next step would be a data normalization. We've got different solutions for stimulants and for destimulants. We've got one destimulant here. We are weighting our data. Then we calculate distance to pattern, distance to anti-pattern, and the coefficient. And now we can sort them using this coefficient. And we can see that once again, the fourth object is the best one. As it was, I think, with two previous methods. Yes. There was like, oh no, this was 649. Here we've got 469. And in Topsys method, we've got 496. So these three objects are the best, but none of them is the best taking all criteria into consideration. So we don't have like a dominant solution in this case. In different methods, we get a little bit different order. And maybe let's practice this. Okay, for a minute, I will stop sharing my screen. Okay. And I will try to share with you the file with data. I hope I will have them. Somewhere here. I think it will be this file. Here. Okay. In the meantime, I've got information from organizers how to share with you my presentation, and I've got it almost ready from the previous two lectures. So I will share it with you when we finish here. And can I upload a file here? Let's see if I can. I cannot put file in here because I'm not probably the organizer of the meeting. So let's check if I can share this with you via this. Yep. I don't have permission. Okay, because I am logged in using my okay. 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 Now it works. You should have access to folders with materials for different classes. Do you have it or not? Or should teachers for particular classes share with you the link to?
Excuse me, what do you mean? If we have the links to
Because there
to
were
participate?
created special Google Drive folders with materials for different classes. This is how we should share our materials with you. But you don't have the link, yes?
No. What
Okay.
exists is that some of the lecturers give us a link in the chat
Okay.
after the lesson.
Okay. So now on the chat, I pasted the link to my
Yes,
folder.
exactly.
I hope it works. And for now, there is only one file, multi-criteria analysis, the Excel file.
Yes, perfect. Thank you.
Check, please, if you can download it so we could work on it. I will give you like 2-3 minutes. I'll be back. I just need to bring something to drink because my voice is getting worse. So I'll be back in like 2-3 minutes. In the meantime, please try to download this file and open it so we could start working on it.
It is an XLS, an Excel file.
Sorry, can you repeat?
It is an Excel file.
Yes, and you can
Okay.
download and open it, yes?
Yes, I have downloaded this. Thank you.
Okay, so I'll be back in 2 minutes and we start working with it. Okay, I'm back. In the same folder, I will share with you presentations from classes. So I will upload it just probably, I hope just after our today's meeting because I've got everything planned. Okay, so I need to open the file myself.
But you have to give us the access to make some differences, some new things in that sheet, because it is only for looking.
Yeah, but you can download it and work on it locally, yes?
We cannot work on it for some reason.
Oh, even if you download it?
Yes, I have downloaded it.
Okay. I will share my screen with you. So if you like press download here. Okay, I was uploading it, but yeah, it was downloaded. And if you open it, you still cannot work on it.
Okay, I enable editing. Thank you.
Yeah, okay, so that was the problem. We need to enable editing, yeah, in most of the Excel files. Okay, these are our original data. So maybe let's start with the pattern approach. In this case, I won't run the presentation itself, but we have like this view what should we do step by step. Got no data preprocessing. We will probably need it. Okay, for pattern and anti-pattern, we need all stimulants. So the first step will be converting the stimulants and nominants into stimulants. So to convert the stimulants to stimulants, we've got this equation. We take maximum minus x plus minimum for this variable. So I've got first sheet with original data. So now I can make the calculations here based on original data because stimulants will have the same values for the stimulant is equal to. Then we've got max function from all the variables, for value of this variable for all objects. I can use dollars here. Then I need to subtract the current value and add minimum value once again for this variable. F4 with add dollars. Oh, no, it's not pattern. It's original, not pattern. I haven't seen that it didn't change me the... Okay. And now I can copy the formula to all other rows. And these are the values as a stimulant. So I can change this into S because after this conversion, this is the stimulant value for my variable. Do you need to see the formula?
Yes.
Okay, so I will show the, maybe I will. No, the formula is here. I hope the screen is big enough so you can see it. So this is the formula for converting the stimulant into stimulant. Okay, can we move to the next step?
Yes, we are.
Okay. So the next step will be converting these nominant values into stimulants. And for this purpose, we've got another formula that includes this R. So we need to first count this R, and then we can calculate the new value. And probably we need to prepare it with the original data. So to calculate R, we definitely need maximum and minimum value for all the columns. Fortunately, for now, I've got all functions has the same names in Polish as in English. But if it will be problem, I will just change my language for my Office software. Okay. And now we can calculate the R coefficient or R variable, R value for, we need it for nominant variables, so for the last ones. And just give me 1 minute. I thought I had it here, but no. Okay. Sorry for this break. C1, C2 that we need for this case are the boundaries for the range. So this is 3, this goes 7. Here we've got 150 and 150. And the formula for R is that this is a maximum value from C1 minus mean values here. I can use dollars in here. In my case, I'm using semicolon to separate the arguments in Excel functions because these are my computer settings. In your case, you may need comma. You need to check in your operating system, or you need to know what is the maximum minus C2. And this is the I should put only not the full absolute, but partially absolute. Okay. So these are the values of R. Maybe I will display this formula for a second, and then we will move on. With the task. 2 minutes and we move. Okay, can we continue? Okay, I hope so. So for nominant variables, and probably this is the moment when I should change my language for the Office software. So just give me a minute. Oh, I don't have English. I hope it won't take much time. I thought that I have it installed on this computer. It will be easier if I will have the English names of the functions, because even if you are using your national languages in Office software, it will be easier for you to find the name of the function having the English language name for the function than the Polish one. So just give me, I hope, 2 minutes to install the software. In the meantime, we can check what's our next step. So we will have if function. We will have some condition. What kind of condition? If our x is less than C1, then we've got first formula. If x is bigger than C2, we've got the last formula. And if our x is between C1 and C2, then we've got only R. So this is the formula we need to write. We need conditional function. That's why I definitely prefer to have it in English. Okay, this is the result we want to achieve. So we are in the process of converting variables to stimulants, and then we need to normalize all the values. So this will be our next step after converting nominants to stimulants. Okay, I was working on this file. I need to save it. Okay, I will stop sharing my screen for a minute. Just to update the software. I hope it will take 1 or 2 minutes, and then we can continue. Sorry for this break. I was sure that I have the English language office on my computer, but probably I was reinstalling the system during summer holidays, and I haven't installed all the required. Right? That was, I think, fast. Now only opening the file. And I should be ready. Yay! Ready. Okay, I've got original data, I've got pattern. So here I will need the conditional function if, and I will basically base on original data. So if my value, the original value, we can once again look at the formula here. If it's less than C1, oh no, this is normalization, we need converting. Okay, less than C1, R minus C1 minus X1. This is what we need. So if X is less than C1, this I need to block. I still use semicolons because I've changed only the language interface for my Office software. I haven't changed the other original settings. So if then our formula will be R I need to also block row 16 minus, then I've got C1 minus X1. C1 also block the row minus X1. And value if false. I still have two conditions to be checked. So I will have internal if function. Now I can check if my X is maybe bigger than C2. If so, my formula is R minus X1 minus C2. And we can assume that in all other situations, so if our X is between C1 and C2, we need to return R. Okay, I don't know what was wrong.
Is a parenthesis missing
Okay, yeah.
somewhere?
Yeah, at the end it's missing the parentheses from the first if function. Yes, at the end there should be two parentheses because the first one closes the internal if function and the second one closes the external one. Yes, definitely. So this is my formula that I can copy to the following rows, and I can leave it like that for a minute displayed. Okay, I can actually also copy it here. And it uses the F column, but the number of rows are okay. So it should be okay. Yeah, I was writing it that I could copy it, and I think I succeeded. So this is the formula, 2 minutes if you need to just copy it or check if your formula is gives the same result. And then we will move on to normalization process. Okay, I hope we can move forward. Basically, if you need me to display something for longer, just tell me. So we've got, these are also now stimulants. Definitely, because we've just converted nominants to stimulants. And we can normalize first. Okay, maybe I will copy this and paste it here. But I don't need the internal values. Definitely, I will have to change them for all the variables. First, I can normalize weights. So it is equal to this divided by sum of all the weights. And I can probably display it like only first three digits after the decimal point. And now we've got normalization for all the variables, and now all our variables are stimulants, so we will use one formula for this. Normalization of stimulant variables. We've got it in here. So once again, for our values, we need to calculate maximum and minimum value. Of course, for the first three, first two, sorry, the values should be the same as in the previous table, in the original table, because they were already stimulants. Fill with that. Or I can with formatting. And in my normalization formula, I need the original value. So I will need the parentheses. Then original value minus minimum value. This I need per column divided by maximum value minus minimum value. Also per column, so I need to block only the row, because now I should be able to copy this formula to all the columns. So I will show for a few minutes, like 1 or 2 minutes, the formula, and then we can check if we actually got the same results as in the presentation, because we should get the same values. Okay, so let's check our results. I'm not sure if I will be able to display the data. Okay, let's display them to 3 decimal points. Okay, I should be able to display it that we see both the presentation and our results. And I think that we got the same results as in here. Definitely. So we've got our data prepared for further analysis. We've got, in this case, we converted all the variables to stimulants, and we have normalized them. So these are the values that we can use in our pattern method. So what is our next step? Is calculating the pattern. And in this case, pattern is a maximum value. And of course, I think it should be 1. If the data is normalized, it should be 1 in all the columns. Okay, this was easy. So now we need to calculate the distance from pattern. So how to calculate the weighted Euclidean distance between pattern for each observation? Well, no, not some. It will be square root. And then we will need some product. Because we will have to, some product, we've got like, first array will be our weights. So we need to multiply our weights. And this will be for all objects. The weights are the same. And then we've got, oh my God. I hope I can calculate it. In one formula. Okay, I will show you once again the formula maybe. How weighted Euclidean distance looks. So we've got this square root, and we've got this sum. This is the first part, the first array, the weights, and the second array is the difference between our x and the pattern squared. So this is what we need to put in our formula. It will be, let's try that. Power. First, we've got number. So it will be x minus pattern. And we got to the power of 2. And I think that's the correct. That's the correct formula. Quite complicated. So this is the formula. 2 minutes to copy it. A little bit complicated, but manageable. Okay. So now, when we've got our distance from antipattern, I will take my object IDs and distance from pattern, And I will sort those values. Okay, object distance. Of course, I need the headers for my data. Custom sort. I need to sort it by distance from smallest to largest. And these are my top 3 objects according to pattern method. Any questions to this method? Okay. I can actually duplicate this sheet and create the anti-pattern approach. Let's see what were the differences for anti-pattern approach. We need anti-pattern. Distance is calculated in the same way. And we need to just change the sorting order. So now it will be easy because we have already everything prepared. We've got original and our current. Yes, everything is prepared to calculate the anti-pattern. We just need minimum values. We've got the results. I want to paste them as values only. Custom sort by distance, but this time from largest to smallest, because we want the distance from the anti-pattern to be the biggest. So what I've done, I copied this spreadsheet and created anti-pattern spreadsheet. I've changed here label to anti-pattern and max to min. And once again, I've copied the class label, object labels and distance from anti-pattern. And then I've sorted it this time in the decreasing order to get once again the 3 best observations in this method. And the third method, the one we will be, I hope, even today doing using the Python and built in Python package for it, is Topsys method, which uses both pattern and anti-pattern. But in Topsys method, we can have actually we cannot have the nominants. So let's see what we need in this case. What form of data we need. These are the original data. We already have it. We need to convert nominants to stimulants. But then data normalization we perform for stimulants and the stimulants. Okay, so maybe I will once again copy pattern. Move or copy. Oopsies. In this case, this variable can be left as the stimulant, so I can copy the original values from here. But in this case, we've got this stimulant value, which should be treated a little bit differently. So let's see. Here we will need at least 2 more rows and columns, sorry. So let's see what we need to have differently. Definitely data normalization is a little bit different for the stimulants. We had it. Normalization. Okay, this is the formula for normalization of the stimulant variables. Max minus x divided by max minus mean. So we need to change this in here because we don't have mean minus x, but we have max minus x for the whole column. And we can ignore the fact that this formula is different than the formula in neighboring columns. And of course, for the stimulant, one second. Because I think something is not as it should be. We've got data prepared. This is the step we already done. Okay, data normalization is different in this case. Different formula for data normalization. Let's check it. So it's equal to original value divided by ASQRT from sum and here we've got our and that's the correct formula for Tops's method. For all the variables, doesn't matter which is the, what is the, if variable is stimulant or destimulant. So these are the weights. I will display the formula for it for a minute. So different normalization formula for Topsis method. We are dividing the original values by sum of squares of all the for values of this variable for all the objects in our model. For the next part, we can do it actually also in here. We can multiply the result by the weight. And for the weight, we need the third row always. And once again, we can copy the formula. So we've got two steps in one. Once again, the whole formula. In the meantime, I will copy this. Okay, maybe I will paste it for the third time. Distance from antipattern. And the Q coefficient. Distance from antipattern. This one and this one. One second, because I think that, okay, no, now it's okay. So we've got distance from pattern, distance from antipattern. Whoa. 1 second. If the values are already weighted, do they need to be weighted one more time? Okay, first data normalization, data weighting, defining the pattern and anti-pattern, and for here is the opposite. So here is mean and here is max. Definitely, this change is important. Ignore error. Yes, and we don't need these weights here. So we don't have sum product, but we have sum because we already weighted the weighted the variables. So that's why we don't need sum product, but we need only sum here. And here will be the same, because we don't need this first Ri, which were weights. We've got only distance from anti-pattern. And then we've got the last part, which is the coefficient. And the coefficient is calculated as distance from anti-pattern divided by distance from pattern plus distance from anti-pattern. And this is the value of the coefficient Q, which will be our variable for making a decision here. I can copy the data from here and here. And I need to sort it in descending order here. No, wait. Ascending, sorry. From the highest to the lowest. Yeah, largest to smallest. So descending order. Okay. 4, 6, 9 is my ranking, so I can compare it. For example, okay, I will add additional column here. With the rank. I can use it also for anti-pattern and for Topsys. What I can do now is sort it by the object from A to Z. Oh, yeah, but it's not a problem. A to Z. And for Topsys, the same. A to Z. And now in the last one, I can have object names, which should be in the same order. Then I have rank according to the pattern. Anti-pattern. And ranking according to the Topsys method. Okay, for example, for some variables, we have in all three methods the same rank with the third object and with the last object. First position and second position are always object either object 4 or 6. Okay. Not. And I need to find the Excel function for okay, but I need it in English. I've got the Polish name, but what? The most frequently occurring or repetitive value. Okay, so this is the one I wanted to get. Maybe. Okay, and not in all cases it gave a good value. I could. Okay, I could calculate like if oh, I can even use if error. Then I could use average, for example. Okay, I want it as absolute values. And let's sort it by this rank. Maybe this is a good indicator for all three methods. Rank from smallest to largest, yes. 8, 9, 10. It actually gave us quite good rank. We've got 4th, 6th, 9th object, then 8th, 5th, 7th, and so on. So we've got like the average rank according to all three methods. And actually we are running out of time. I thought that it will take us less time to calculate it in Excel, but if we understand how it works in Excel, it will be easier to apply this method in Python. But definitely we will do this in Python. My question is, because we won't in 10 minutes, we definitely won't do it. And you probably have next classes later, at least some of you. Why is it? Oh, here it is. Yeah, after this course, there are like supervised and unsupervised learning classes. Yeah, okay, I can upload this Excel file after calculations, definitely not a problem. I've got it all, I think I've got it all sorted out, and even the name is changed, so I will just immediately upload it.